All right, this lecture is on how we use the definitions of velocity, acceleration, and average velocity in order to combine those things mathematically to derive a few equations that will help us relate the different quantities of initial position, initial velocity, final velocity, acceleration, and time for objects that are moving in either one dimension initially and two dimensions later on. If you look up at the top here, you see we have a definition of average velocity as distance equals velocity times time, or delta x over delta t equals average velocity. We call that equation 1. We have the definition of acceleration that's been rearranged. We have final velocity equals initial velocity plus at, which we call equation 2. And then average velocity equation for when we have constant acceleration. So we have final velocity plus initial velocity over 2, or 1/2 of Vf plus V naught. We call that equation 3. So if we start with equation number 3 initially, that's a constant accelerated case, like a cart going down a ramp that is at a constant angle. And then we use equation number 2 and we substitute this V naught plus At for Vf into this equation. So that we get 1/2 of Vf plus V naught, right? And we have that equal to average velocity or change of position over time. Now if we multiply through all that by delta t, we get change of position equals average velocity times change in time equals 1/2 of Vf plus V naught times delta t. Now if we distribute the 1/2 across that quantity and the delta t across that quantity, we get 1/2 of 2V naught plus delta t plus 1/2 a delta t squared. And then if we collect some like terms and eliminate some things, we get change of position equals V naught plus or times At plus 1/2 of At squared, which we commonly write then as, rather than change in position, we write final position equals initial plus initial velocity times time plus 1/2 At squared. We call that equation number 4. This equation is particularly useful when we have objects that start at the top of a ramp, or if we drop an object in the air. When it starts at rest, my initial measuring position will be 0. My initial velocity, if it starts at rest, will be 0. So I end up with the distance it falls, right, or final position equals 1/2 of At squared. Right? So that's a pretty common use of that equation for a lot of different cases. Once again, that equation, x equals x naught plus V naught t plus 1/2 At squared. That one can now be added to the definitions of acceleration and velocity and average velocity. Another common equation using those same three that we started with, right? Definition of average velocity, definition of acceleration, definition of average velocity at constant acceleration. Right? We solve equation number 2. Rather than solving it for Vf, this time we solve it for t. Right? So we look at t equals Vf minus V naught all over A, and we substitute that into this equation once again, which is average velocity. See, we get change of position equals average velocity times time. This is Vf plus V naught over 2 times t. Right, now we're going to substitute for this time, this Vf minus V naught over A. And when we do that, then we get our initial Vf plus V naught over 2, which is average velocity, times time. And then we're going to multiply both those together, those two fractions, to get V naught plus Vf times Vf minus V naught all over 2 times A, which puts us here. We'll continue to the next slide to look at that particular equation. Now, if I multiply both sides of this equation by 2a, the 2a will disappear here and it'll appear on that side as 2a delta x. And then notice I have two binomials, Vf, V naught plus Vf, and Vf minus V naught. If I use FOIL, right, remember that old algebraic terms, firsts, outsides, insides, and lasts, I get V naught times Vf is V naught at Vf. Vf times Vf is Vf squared. first insides, the outsides, V naught and minus V naught squared, and then the last one's VF times V naught. So I get V naught VF positive and V naught VF negative, and those cancel out, right? Which leaves me with then 2A delta X equals VF squared minus V naught squared, which is more commonly written as VF squared equals V naught squared plus 2AX, which can be used to relate final velocity, initial velocity, acceleration, and distance. And that gives us then 5 overall equations. The definitions of average velocity, acceleration, right? This is the definition of acceleration again. Then we have position time equation, which relates position, initial velocity, acceleration, and time. We have finally one that relates velocities, initial and final, acceleration, and distance. So no final velocity here, no time here. Right? And those 5 equations can then be used to solve and resolve any sorts of questions we might have, right, regarding the motion of an object in terms of how its position changes, its velocity changes, how long it takes for those changes to occur, as well as what acceleration might be occurring during that time.